Okay, good morning and welcome to the last day of Strings in Vienna. Before we start, a few announcements. So the total number of COVID cases is now 7, so there are 2 new ones, so please keep careful. I know it's the last day, but still, let's not drop our masks and our guard. Posters start falling down, so the local administration took some of them and put them in the conference office, so if you want to take back your poster and you're missing it upstairs, then it's downstairs in the conference office. If your poster is still up there and you want to take it back, then please take it down. And finally, if you want to print something, in particular boarding passes or testing results, you can do so in the... to Veronica.
Okay, so welcome back to the last day of this wonderful conference. So we'll get started with Francesco Benini from CISA, who will tell us about the black hole microstate counting in AdS.
Okay, thank you very much. Good morning. So, first of all, let me join the other speakers in thanking the organizer for the great work organizing this conference. I'm enjoying it very much. So what I would like to do today is to review some recent developments in our understanding of BPS black holes in anti-de Sitter space, in particular understanding their entropy and counter on their microstates. Now for this review I decided to focus on certain aspects, so maybe I will not be able to cover all possible aspects of this story, and apologize in advance for this. Moreover, I'm sure I forgot some references, so once again I apologize in advance for the references that I missed. Now, this topic has been extensively studied in the context of BPS black holes in asymptotically flat spacetime, starting with the seminal work of Strominger and Waffa, who showed that string theory reproduces the entropy of BPS black holes in asymptotically flat spacetimes. And since then, there has been a tremendous work, as we heard, for instance, a little bit in the talk of Luca Eliesu, and in very accurate and impressive computations has been done in that context. Lots of people worked on this subject. The long list of names of people that work on it couldn't fit on this slide, but it's a long list. On the other hand, AdS-CFT provides us with a fully consistent, complete, and non-perturbative definition of quantum gravity in anti-de Sitter space in terms of an ordinary quantum field theory that lives in the boundary. This is a description that we lack for string theory in flat space. And for that reason, it is interesting to ask about black holes in anti-de Sitter space and how much can we push this program. So this is what I will review today. Let me say up front that AdS3 and AdS2 are very special for many reasons. In particular, AdS3 has been studied from the very beginning of the story. AdS2 is the focus of recent research, as we heard in this conference. And in my review, I will consider AdS in 4 and more dimensions. Moreover, I will be interested, and most of the literature is interested in this, in a sort of semi-classical regime for gravity, in which gravity is weakly coupled, so AdS is much larger than the Planck scale, and moreover, gravity is close to Einstein gravity, so the scale of higher derivative corrections is much higher than the AdS scale. This is not the only interesting regime. For instance, the tensionless string that has been studied by Gabriel, Gopakuman, Eberhard, and other people is also very interesting, but here I will focus on this regime. And in terms of the boundary quantum field theory, it means, first of all, that the quantum field theory should be at large n, and this is nice, this is an interesting limit. But moreover, the quantum field theory should be strongly coupled. And so in particular, if you want to use the quantum field theory as our definition of quantum gravity in the bulk, and we want to perform computations in quantum field theory because it is non-perturbatively well-defined, then of course this poses a problem. But nowadays we have at our disposal a lot of non-perturbative methods in quantum field theory that we can use to perform these computations. Here I'm listing a few, for instance, the conformal bootstrap, integrability, supersymmetry, numerics, and so on. And most of the literature has focused on the tool of supersymmetry, which is very powerful, and this is what will mostly appear in this review. Okay, so we know that black holes have an entropy. This is the Bekenstein-Hawking entropy. It's proportional to the area of the horizon. Now, this entropy means that a black hole represents an ensemble of states, and so this should correspond to an ensemble of states in the dual quantum field theory. And so this allows us to define a quantum entropy as the logarithm of the number of microstates. This quantum entropy will start with the Bekenstein-Hawking contribution, but then we'll have a lot of corrections, and the correction will be one of the focus of this review. So we'll tell you what are our developments in understanding all of these corrections from the point of view of the boundary theory. In particular, there will be, well, we expect that there will be perturbative corrections from loops of fields in the bulk, higher derivative corrections from, for instance, from massive string modes, classical non-perturbative corrections from classical saddles of the classical gravitational theory, but also stringy non-perturbative corrections. And we will see all these ingredients later on. Now, before we start with the details, let me put up front some caveats of this discussion. So first of all, most of the literature discusses large black holes in AdS. These are black holes whose size is comparable to the size of AdS. Now, these black holes are interesting. We can study their quantum properties, but we should keep into account that they have other properties that are different from small black holes. Small black holes, which are much smaller than AdS, are perhaps more similar to black holes in flat space. But for instance, small black holes have a negative specific heat. Large black holes have a positive specific heat. Of course, in the supersymmetric context, this will appear in a different way, but we should keep in mind that there are differences. Another caveat is that if we want to use the boundary quantum field theory to understand the microstates of these black holes, we should keep in mind that this theory will capture all states in the bulk. Of course, not just the states of the black hole, and this will appear in the following discussion. Okay, very good. So how do we count states? Well, we can construct the generating function for these states, a grand canonical partition function. This is a sum over all the states over some fugacity that keeps into account the charges of the states. And if we have this object, we can essentially follow two strategies. One is a more Lorentzian approach. We can extract the degeneracy of states from this grand canonical partition function with a Laplace transform, and assuming large degeneracies, this reduces to a Legendre transform, and we can try to extract the entropy. Or we can take a more Euclidean point of view. We realize that the grand canonical partition function is an Euclidean path integral in which the time circle is compactified. And by the rules of AdS-CFT, this should be identified with a path integral of string theory in the bulk. We don't really know what this object is, but you can use the quantum field theory to define for us this object and try to interpret properties of this object, maybe rules that we should use to construct this object in a semi-classical expansion and so on. Okay, so we want to compute these partition functions, but as I said, in the regime that will be of interest here, we are at strong coupling. So what do we do when a strategy that has been extensively used in the literature is to exploit supersymmetry? So construct a supersymmetric version of the partition function. So we insert -1 to the fermion number here, and then we obtain a protected object. An object that can usually be computed exactly either by moving the theory to weak coupling if there is a weak coupling limit, because these objects do not depend on the couplings, or if you don't have this limit, we can use supersymmetric localization techniques. So these are very interesting objects that we can study. These objects, these are Witten indices, though they only depend on BPS states, and for these reasons, at least at face value, this object is useful for counting the states of BPS black holes. Now, an obvious question is, okay, does this index capture the full entropy? Because this index is counting bosonic minus fermionic states, so one can expect cancellations, or perhaps large cancellations. But at least in leading order, we can answer this question, and the answer is yes, this index does capture the full entropy. And in fact, one can make an argument using the fact that for an extremal black hole, there is a near horizon AdS2 region, and this region has a superisometry, which is SU1, 1/1, and one can use this isometry to argue that under a suitable combination of the fermion number and the charges, all the states have the same, get the same phase. And so they all contribute in the near horizon region to the entropy. In fact, this argument is very similar to an argument that Sen made for black holes in flat space. In that case, there is more supersymmetry and the superisometry is larger, but the argument is similar. If we don't like this argument, in fact, one can confirm this expectation by an analysis of the two-dimensional effective action, as we heard in the talk of Luca Elieso, and the conclusion is the same. So, okay, so one has to compute some supersymmetric partition function, but which partition function? And in order to understand that, one can use the rules of holography. So one can interpret a black hole in AdS as a sort of holographic RG flow that starts with the UV theory, then deforms this theory, and the black hole describes this RG flow. And then one can use the rules of AdS-CFT to derive what is the deformation of the boundary theory, which is induced by the presence of the black hole, and so understand what is the specific partition function in which the field theory lives. And if you do this exercise, essentially, loosely speaking, we find two classes of black holes, BPS black holes. One class is given by BPS black holes with a magnetic charge for the R symmetry. On top of that, there can also be electric and magnetic flavor charges or rotations. But this magnetic charge is very important because essentially what it does, it topologically twists the fermions along the horizon. And so this is the way in which this black hole preserves supersymmetry. And then if you go to the boundary theory is topologically twisted. So for this class of black holes, the object that one has to study is a topologically twisted index, or a topologically twisted partition function. On the other hand, there are more ordinary or more standard BPS Kerr-Neumann black holes. These are rotating black holes. On top of that, they can have electric and magnetic flavor charges, and the deformation that is induced on the boundary theory is the one of the superconformal index. In fact, as we heard in the talks of James Sparks early this week, we can name a third class of black holes, which is spindles that preserve supersymmetry in a different way. However, we already heard about those, so I will not talk about them more in this review. All right, so what I would like to do now is, instead of going through the many examples that have been studied in the literature and will mention the main directions that have been followed, I would like to focus on two examples, because these are two examples in which we will see the main features and the main progress that has been made and the main ideas that have been developed quite concretely. So for the sake of concreteness, I will consider these two examples. I will not consider a single example, because it turns out that in different examples, different aspects have been understood better than in the other, but with two examples we will be able to cover the main ideas that have been developed. So the first example that I would like to discuss is in AdS4, magnetically charged black holes in AdS4. The second example will be in AdS5. So these black holes, these magnetically charged black holes, are very nice because they are simple. In particular, the simplest black holes can be spherically symmetric and static. So this is what is nice. They are BPS. They preserve one complex supercharge. So in particular, notice that black holes in AdS preserve less supercharges than black holes in flat space. In flat space, we have 4 or 2 complex. And these particular black holes have been constructed by Cacciatori and Clem. They were constructed in 4-dimension n equal to U1 to the 4 gauge supergravity, which uplifts to 11-dimensional supergravity in AdS4 times S7. And these black holes are quite simple. I'm not specifying the radial profile of these functions, but as you see, these are static, so they are simple. The important point is that there is magnetic flux for the R symmetry along the horizon. And on top of that, as I said, one can add electric flavor charges and angular momentum. Now, these black holes have some Bekenstein-Hawking entropy, which is given by the area of the horizon. Moreover, there is a dual theory, the dual theory 3-dimension n equal to 8 ABJM gauge theory, which is a theory which gauge group UN level 1 times UN level -1. And there is the standard relation between the rank of the group and the size of AdS. And in fact, I already used this parameter n here in the entropy. And because of the presence of this black hole, this theory is topologically twisted. Okay, so we want to compute some grand canonical partition function. As I explained in this class of example, this is a topologically twisted partition function. So this is essentially a Witten index, which is a trace over the Hilbert space of states on the S2 with topological twist, and one can refine this partition function with fugacities for the various symmetries. Now, as I said, what is nice about these supersymmetric quantities is that they are protected, so they can compute it exactly. And this is a typical form of the expressions that one obtains with localization. It is some contour integral, and then there is some integrand, which follows from a one-loop computation in the gauge theory. The variables here are complexified holonomies for the maximal torus of the group. So this is an exact expression at finite n, and one would like to study the Largen limit of this expression. This can be done in various ways. One way is because this is a contour integral, one can essentially use Cauchy theorem, so identify the position of the poles and then collect the residues. And if one writes down the equations that control the position of the poles, this turns out to be an equation that looks like the Bethe-Ansatz equation of some integrable system. So here are the equations. So one would like to solve this equation at large n. This can be done numerically, and what one observes is that the solution of this equation distribute themselves along some curve in the complex plane, so the behavior is very similar to what we have in matrix models at large n. And one can proceed in a similar way, so in the large n limit one can substitute the distribution with a continuous distribution with some density of eigenvalues, and this can be solved. Here I'm plotting some comparison between analytic results and numerical results, and then plugging back and computing the residue, one obtains some expression. So in this case, this is the expression that one obtains, but it's very simple. So this expression starts with n to the 3 halves. So this is precisely the same order as the Beck-Einstein-Hawking entropy. It is a particular function of the chemical potentials. Here is delta chemical potential. These Na are magnetic charges. And in fact, it turns out that this is precisely the free energy of the black hole, in the sense that its Legendre transform exactly reproduces the Beck-Einstein-Hawking entropy. It is the free energy of the black holes also in the sense that one can compute the on-shell action for these black holes. This requires some regularization, as we heard before in the talks of James Sparks. But this can be done, and this precisely reproduces the free energy of the black hole from the gravitational point of view. In fact, one can make a stronger connection with the supergravity, because it turns out that this extremization that produces the Beck-Einstein-Hawking entropy is dual to the attractor mechanism in AdS4. What do I mean by that? Well, if you want to determine what is the near horizon geometry of these black holes, you want to determine what are the expectation values of scalars at the horizon. So you have to solve some supersymmetry equations, and the supersymmetry equations can be put in the form of an extremization problem, in which you have some function that you have to extremize. The extremal value of this function turns out to be the area of the horizon, and in fact this function is precisely the same function that appears here. Okay, so this strategy, or similar strategies, have been applied in a variety of examples of black holes, many different black holes of various types, in different dimensions and in different theories. And in all these examples, this strategy works in the sense one identifies some suitable supersymmetric partition function whose value at large n reproduces the free energy and then the Beck-Einstein-Hawking entropy of the black holes. So I don't want to list all the examples that have been studied, but let me highlight some interesting directions. So first of all, for the black holes in AdS4, as I said, they can be generalized with electric charges and angular momentum, so one can study more complicated and interesting black holes. One can study more exotic black holes in which the horizon is not a sphere, but in fact is a Riemann surface, and study their behavior. Of course, one can study black holes in more general theories. So, for instance, one can consider different internal manifolds that are not S7, but other internal manifolds. One could study other theories. For instance, one could study massive type 2A. One could study other constructions in which, for instance, these black holes are realized by M5 branes wrapped on some 3 manifolds, and so on and so forth. Of course, one can move to other dimensions, and in fact, black holes in AdS5 and in AdS6 with topological twist has been studied. And then in the context of Kerr-Newman BPS black holes, essentially all the cases from 4 to 7, from AdS4 to AdS7 has been studied. And in the second part of my review, I will talk about the case of AdS5. All right, so we understood that Bekenstein-Hawking entropy can be reproduced from the boundary theory. What about corrections? And from the point of view of field theory, it's pretty clear what we have to do, because as I said, we have an exact object, so the problem is mathematical. We have to compute these objects at large n and see what we obtain. However, it turns out that computing corrections to this object analytically is quite difficult. And so what people did in the literature, in particular these two groups here, was to resort to a mix of analytical and numerical tools. Essentially what they did was to solve these Bethe-Ansatz equations with very high precision numerically, doing that for a large number of values of n and large values of values of the chemical potential, and then try to fit some behavior and extract what is the behavior of this partition function. And this is what was found. We will improve on this in a moment, but this is what was initially found. So the leading contribution is the Bekenstein-Hawking contribution that goes like n to the 3/2 in this example. Then there is a term n to the 1/2. There is a logarithmic term, and then the series continues in 1 over square root of n. Now, the author were not able to identify these functions explicitly. However, in the SO8 symmetric case, in which all the chemical potential are equal, they were able to do that. And in particular, they were able to consider a slightly more general situation that I mentioned before, in which the horizon has the shape of a more general Riemann surface, and one considered the internal manifold as 7 mod zk. So this allows us to have some more data points and some more parameters here that can be compared with the field theory. So what I would like to show to you is that, in fact, this correction here turns out to be a higher derivative correction. And this correction here turns out to be a one-loop correction. So let me start with the one-loop correction. We already heard about these corrections in the talk of Luca Eliesu. These log corrections to the entropy have been extensively studied in the context of black holes in flat space. In fact, Sen did pioneering work on this, and as he wrote, this correction is interesting because he gives us a window into quantum gravity. Because the Bekenstein-Hawking entropy only knows about the area of the horizon, it doesn't know anything about how many fields there are in the theory. We could have 1 million fields which are not activated, but this log correction instead is sensitive to the fields that we have in the theory. Now, an interesting fact that happens in this example, and it is related to the caveat that I mentioned before, is that this log correction in AdS4 turns out to get a contribution not just from the near horizon region of the black hole, but from the whole space. So this log correction does not come from the black hole alone, it really comes from the whole space. So this is something that we have to take into account if we want to compare with field theory. Now the computation, so one can do the computation. This was done by these people here, and essentially the computation that Luca showed early this week. Here one has to do the computation in 11-dimensional supergravity. There is some nice simplification because in one dimension only the zero modes contributes, so this simplifies the story. Of course, one has to examine all the fields in 11-dimensional supergravity. Now it turns out that the number of modes that contribute to this logarithmic term is controlled by a cohomology of L2 harmonic forms, because of course the space is non-compact, and also the Euler characteristic of the horizon will appear, because that will be proportional to the number of harmonic forms. And in fact, putting all the coefficients together, one finds this coefficient here with precisely matching with the field theory computation. What about the other term? Well, as I said, it turns out to come from higher derivative corrections. So these people here studied 4 derivative corrections for dimension n equal to minimal gauge supergravity. And it turns out that in this theory there are 2 higher derivative corrections. One is constructed with the Weil multiplet, one is constructed with the so-called T-log multiplet. And in principle, one should, first of all, compute the correction to the solutions that come from the fact that the action is, the theory is corrected by either derivative corrections, and then evaluate the on-shell action on these solutions. This is probably quite difficult to do analytically, especially to compute the higher derivative corrections to the black hole solutions. However, there is a nice feature that appears in this theory, which, however, seems to be an accident of the four-dimensional minimal gauge supergravity, is that any solution to the two-derivative action is also a solution to the four-derivative action. And so one does not have to compute from scratch, to compute the corrections to the solutions. And this allows to write down a very compact form for the on-shell action. This form depends on various coefficients. So the coefficients that here are called f and chi depends on the geometry. These essentially are the evaluation of the two derivative and four derivative terms on a given background. The coefficients A, B, and C depends on the theory. So they are the coefficients of the higher derivative and two derivative corrections in the action. Now, in principle, one would have to start in 11-dimensional supergravity with higher derivative corrections, and then do the consistent reduction, the consistent truncations to 4 dimensions to see what are the coefficients in front of the higher derivative terms. And this is probably quite difficult to do, although I think that there is work in progress in that direction. However, what the authors did was to use a trick, essentially to use one example which has been studied with very high accuracy. This is the example of the BJM put on S3, so the S3 partition function of the BJM theory. This has been computed with very high accuracy by Marigno, Putrov, and Drucker. And using this example as a data point, they were able to fix this coefficient here, and then one can evaluate and compute the first correction and order n to the 1/2, and in fact this precisely matches with the field theory computation. Now, of course, at this point, it would be very nice to add generic fugacities and match the more general formula. However, this requires to add vector multiplets to this theory, and this is a more complicated theory, and this has not been done. It's an open question that should be addressed. Nevertheless, this group of people were able to put out a conjecture for what should be the Largan limit of the topologically twisted index to all perturbative orders in 1/√n up to non-perturbative corrections. They did that with a heroic numerical effort in which they, once again, they computed with for a large number of values of the parameters with very high precision this partition function, and then I don't know how they come up with this formula. But here is the formula, and this is very interesting. So you see this n hat is a renormalized, essentially renormalized values of n. And if you use this n hat, you have an n hat to the 3/2, n hat to the 1/2, a log n, a constant term, and then the series truncates up to non-perturbative corrections. So this, of course, if you use the values of n, you will have an infinite series in 1/√n, but in terms of these renormalized values of n, this does not happen, and this seems to point in the direction of some renormalization theorem, but this is something that has not been understood, and this is an open question. Okay, so now in the second part of my review, I would like to move to a second example, which is the example of Kerr-Neumann black holes in AdS5, in which other aspects will appear. So the beginning of the story is very similar. One can study rotating, this time electrically charged black holes in AdS5. In fact, these are the black holes of Gutowski and Real that were later on generalized by various people. These are black holes constructed in 5-dimensional, n equal to U1 gauge supergravity that uplift to type 2b supergravity in AdS5 cross S5. These black holes have some angular momentum and some electric R charges. And once again, they preserve one complex supercharge. They have some Beck-Steinhausen entropy. And what has been mostly considered in the literature is the case of large black holes in these theories. So black holes whose size is comparable with AdS. And for these black holes, all the charges scale like n squared, where n will be the rank of the group in the dual theory. The dual theory, as we know, is for dimension n equal 4 superior Mills. And as I explained before, it turns out that in this, for this class of black holes, the relevant grand canonical partition function is a superconformal index that counts with sign BPS states on S3 or equivalently protected operators of the superconformal algebra in flat space. For this index, we can give a Hamiltonian definition, which is a standard one. Here, P and Q are chemical potentials for the angular momentum. Y are, these are fugacities for the angular momenta. Y are fugacities for the flavor charges. And one can use also chemical potential, tau and sigma for the angular momenta, and delta for the electric charges that will appear in the following slides. In fact, it turns out that it's convenient to introduce one more chemical potential with a relation, because this makes the formula easier. Alternatively, one can use a path integral definition of this object as an Euclidean partition function on S3 times S1 with a suitable background. So once again, this is a protected object. We have an exact formula for it. This formula is here. It is once again an integral of the maximal torus of the gauge group. The integrand is written here in terms of some special functions, which are elliptic gamma functions. But essentially, this is the generating function of all the strings of BPS operators that you can write down. And then eventually, this integral is going to pick up the gauge invariant operators out of all the strings that you can write down. So now one has to study the Largen limit, and the Largen limit of this object turns out to be tricky. In fact, one saddle point was found long ago. This is a saddle point in which the flat gauge connections are real. This saddle point describes a gas of gravitons in AdS, but it does not describe black holes. However, since then, many different approaches have been developed to understand this Largen limit, and now I would like to review what are these methods and which results one can obtain using them. So a very powerful method is the so-called Cardy limit. And this stems from the observation that we take a high temperature limit, by which I mean a limit in which the size of the S1, the temporal Euclidean circle, goes to 0, then the integrand simplifies a lot. More specifically, this will be a limit in which the angular chemical potentials go to 0, the electrical chemical potential go to the real line, and in terms of fugacities, the fugacities live on a disk. This will mean that the angular fugacities go to 1, the electrical fugacities can go to the boundary of the disk. And it turns out that the integrand simplifies a lot. In fact, it's controlled essentially by one polynomial. This is the most diverging term as tau and sigma goes to 0. So this is a polynomial, and in a suitable range of the chemical potentials, this polynomial has a is a local minimum at u equal to 0, and then one can just use the point approximation and obtain the result. And then from there, it is straightforward to take the Largen limit. And once again, one obtains a very simple answer. Once again, this answer scales, if you want, the free energy scales as the Bekenstein-Lonkin entropy. And in fact, this turns out to be exactly the free energy of the black holes, whose Legendre transform is the Bekenstein-Lonkin entropy of the black holes. Now, here we took a limit, and in terms of counting of states, this is precisely the same limit as the two-dimensional Cardy limit. This limit captures the degeneracy of states whose charges are much larger than the central charge. So in this case, this will be black holes whose size is much larger than the typical size of AdS. Now, in fact, this limit has nothing to do with large n. One can study this limit even at finite n or small n. And moreover, can be studied in very great detail. Now, it is perhaps a bit surprising at the beginning that there is a Cardy limit in 4 dimensions. Of course, in 2 dimensions, we have a Cardy limit. This follows from modular invariance. It allows us to relate the Casimir energy to the density of states for high charges. Now, in 4 dimensions, there is no modular invariance. So perhaps one would not expect that there is a Cardy limit, but in fact, there is, and in particular for supersymmetric theories, it is very much under control. And moreover, this Cardy limit, so the density density of states is controlled by central charges once again, or anomalies. So this is a very robust object. And in fact, the way in which this can be obtained is not through modular invariance, but it is obtained by doing the reduction on the circle and obtaining an effective theory on the tree sphere and studying very carefully what is the effective theory of these modes. Now, if you consider the vanilla case in which you have S3 times S1, it turns out that you might have various zero modes, which have to be quantized and has to be studied. So this is still a slightly complicated system. But if you consider a twisted case in which the S3 is twisted as you go along the S1, it turns out that all the modes are massive, even the gauge modes that usually do not get a mass. In fact, what is generated is a Chern-Simons term in the effective three-dimensional theory, and this is a Chern-Simons theory that has precisely one trivially gapped vacuum. So this allows to make a very detailed computation, and in fact, for the so-called R-charge index, or index on the second sheet, a very explicit formula was obtained. So what is this index? Essentially, the only modification with respect to what I said before is that instead of writing -1 to the f, you write -1 to the R symmetry. And in fact, this just corresponds to shifting tau into tau plus 1 and using the fact that this partition function is not single valued on the disk of fugacity, there are branch cuts. So this corresponds to going through the branch cut on another sheet. And this object is very much constrained. So in fact, here is the full perturbative expansion of this object up to non-perturbative terms. The most singular term goes like 1 over tau squared, and then it goes down all the way to the power tau, and then this perturbative expansion stops. So this is a very powerful result. Now, for n=4 superior Mills, and also for some other theories, it turns out that one can more generally study not just the limit when the fugacity goes to 1, or if you want the chemical potential go to 0, but when the chemical potential go to rational numbers. And this is a very interesting story here that is related to non-perturbative corrections. Okay, so these are very interesting limit one can take, but more generally, one might be interested in relaxing this limit and studying just a large n limit with no limit on the fugacities. This can be done, and in fact, it reveals interest in non-perturbative corrections. There are many tools that have been devised to compute this limit, so I will start using one to tell you what results one obtains, and then I will comment on other methods. Okay, so one method, essentially all this method relies in writing the expression for the superconformal index in some different way that allows different manipulations. So one of these ways is the so-called Bethe-Ansatz formula. This formula works best when the two fugacities for an angular momentum are equal. So that means it's, these capture states in which the two angular momenta are the same. And in this formula, there is no n integral, but there is a sum. And this sum is over the solutions to some equations that once again resembles Bethe-Ansatz equations. In this case, they resemble Bethe-Ansatz equation of an integral of elliptic integrable system. Once again, the variables are complexified holonomies for the maximal torus of the gauge group, and this holonomy lives on a T2, and one should solve this system. Now, what is different in this example in AdS5, and this is a difference that made possible to make interesting progress, is that we know of exact solutions to these equations. In fact, we know about a family of discrete solutions. These are labeled by two numbers. And essentially, these solutions correspond to distributing the eigenvalues on some cycles of the torus, or wrapping multiple times these cycles. Now, there is a simple solution that here I call basic solution, in which these eigenvalues are along the B cycle of the torus. One can study the large n limit of the contribution from this solution, and it turns out that this precisely reproduces essentially the same formula that we saw in the Cardi limit. This is the free energy of the black hole that captures the Blackenstein-Hawking entropy. But what about all the other solutions? So one can study the limiting behavior of all the other solutions. They all go like e to the n squared. So the sum of all this contribution looks like a semi-classical expansion. And in fact, one can work out what is the limit, the behavior of these solutions. This is what one finds. So there is a term that goes like n squared. there is a term that goes like log n, then the series truncates, where there is an order one term, the series truncates, and then one is also able to identify non-perturbative corrections, in particular the exponent of the non-perturbative corrections, not the coefficient in front. And as I would like to argue in a moment, in fact, well, first of all, this sum is precisely a semi-classical expansion in classical gravity, and moreover, this correction, as you can see, can be identified as one-loop corrections and stringy correction from Euclidean D3 branes. So let's first look at classical non-perturbative corrections that come from classical gravity. Well, from the point of view of the bulk, one fixes the boundary conditions, and then one looks for solutions in the bulk. And it turns out that there exists an infinite family of complex Euclidean solutions of the supergravity theory, type 2b supergravity. So these solutions are supersymmetric, but they are not extremal, and this is possible because these solutions are complex. In fact, one can evaluate the on-shell action of these solutions. These require some regularization, but can be done. And the on-shell action precisely reproduces the order n squared contribution the one obtained from the field theory. Moreover, one can also identify a class of non-perturbative correction, stringy correction, that come from Euclidean D3 branes. These Euclidean D3 branes wraps an S3 inside S5, and they wrap an S1 inside S3. These D3 branes live at the horizon. Well, here we are in Euclidean signature, but they live at the horizon. One can compute the on-shell action of these D3 branes. And in fact, this on-shell action precisely reproduces the non-perturbative correction that I showed to you before. Just to give you some more detail, well, essentially the contribution of these D3 branes, one should sum the contribution of the pure geometry, the contribution of the geometry with a single D3 brane, with two D3 branes, and so on. And in a regime in which the contribution of these D3 branes is exponentially small, one can bring everything in the exponent, and the correction precisely looks like a non-perturbative correction to the free energy. However, if this correction is not exponentially small, but is exponentially large, and this will happen when the imaginary part of the action is negative, then this will be a diverging series with exponentially large contributions, and so this seems to signal that there is some condensation of D3 branes in which the solution is driven to some other classical solution, and so the contribution for this complex solution should not be added to the path integral. So one can try to formulate a criterion like this for which complex solutions to supergravity should be included in the semi-classical expansion of the path integral. And in fact, what happens is that the supergravity has many more solutions than the contribution that appear in the field theory. However, applying this criterion to retaining only the solutions for which the corrections from D3 branes are exponentially small, so the imaginary part of the action is positive, this precisely throws away the unwanted solution and keeps only the solutions whose contributions appear in the expansion of the field theory answer. Okay, so what about perturbative and higher derivative corrections? Well, these corrections are not understood at the same level of precision as in the AdS, for example, so there is some work to do here. However, so the logarithmic term, this was evaluated in the case of the basic solution. So more precisely, this was evaluated in the Lorentzian signature, essentially taking the analytic continuation back from Euclidean to Lorentzian. This is just the Lorentzian black hole, and then the Cardi limit, applying Kerr CFT and evaluating the contribution. And in fact, this computation can reproduce this logarithmic term with the correct coefficient. So this suggests that, in fact, in this particular example, there is no contribution to the logarithmic term from the bulk. All the contributions just come from the horizon, because this is a near-horizon contribution calculation. So this is nice, but of course it would be nice to have, to being able to perform the computation more generally in the full bulk, and for all the various complex solutions, all the various contributions. So this is some open question. What about the perturbative terms? So in this case, there is no order n contributions. And in fact, this matches with the fact that has been argued that the first higher derivative correction vanishes for this particular observable. However, there is an order 1 term. This order 1 term is expected to come from a one-loop computation, not just the logarithmic term, but the full contribution from a gas of gravitons that is hovering outside of the black hole. And let me mention at this point that, for instance, this is a contribution in which the cancellation of states happens. So in this case, the supersymmetric entropy will not be equal to the entropy. Once again, also in this example, we see that the series truncates at order 1, so there are no further perturbative corrections to this observable. This is also compatible with the Cardy limit, in which very detailed computation can be done, and once again, it is not at present clear why this happens. So this is an interesting question that would be nice to answer. Okay, so now I would like to comment on the other approaches one can obtain to study this system. And one would like to study this system, this integral, just in the saddle point approximation without relying to strange manipulations. And in fact, it turns out that this can be done, but one way to do it involves a very interesting class of matrix models. So these people here manipulated the integral that I showed to you before, and they brought it to the following form. So this is a class of matrix models in which the potential is the sum of two terms. One is a periodicity with period sigma, one is a periodicity with period tau. And it turns out that this matrix model admit a family of saddle points in which there is a distribution of eigenvalues, but the eigenvalues are not distributed along a line, they are distributed on a surface. And in fact, in this case, it's a parallelogram. So this is quite an interesting class of matrix models with which I guess we are not so familiar, that I think will deserve more study. One can evaluate the contribution from these saddles, and this precisely reproduces the results that I showed to you before. In fact, there is a family of saddles, and these saddles essentially generalize the case tau different from sigma, the solutions, so some of the solutions that I showed to you from the Bethe-Ansatz equations. It's also nice to see that these solutions only exist for certain ranges of the chemical potentials, and if one looks in which range of ranges of the chemical potential the solutions exist, this precisely matches with the criterion of D-triple instability that I showed in the bulk. Now, in all these approaches, there seems to be other potential contributions to the grand canonical partition function. Using the Bethe-Ansatz equations, we know that there are other solutions to the Bethe-Ansatz equation that I don't wrote in the previous slides. These are some continuous families of solutions. From the point of view of applied and saddle point approximations, there exist multi-cut solutions with filling fractions. So these solutions are poorly understood. At the moment, we do not know if these solutions will have a nice Largen limit or no, but if they do, this will hint towards the fact that there should exist new BPS solutions in the bulk, so new BPS black hole solutions of some sort, and if this is the case, it would be nice to find them. And I will comment more on that in a moment. So now I would like to discuss some other expansions, interesting expansions that one can do. So one is a truncation of the Platistic exponential. What do I mean by that? Well, the very same integral can be written in the following form. In fact, this is the first form in which the integral was, the formula for the index was written. In this expression, this function f is the so-called single letter index. So this is the generating function for BPS fields in the Lagrangian. And this object here is a combinatorial object that essentially counts all possible strings of fields that you can construct. And then this integral over the gauge group just selects the gauge invariant ones among all these strings. So this captures all multi-trace operators that one can construct with the BPS fields in the Lagrangian. Now, this is the very same integral as before. However, now one could take just the first term in this expansion, or the first two terms, or the first three terms, and so on. And this simplifies a lot, this integral, and this can be studied. And in fact, these people showed that already taking one or two terms gives a fairly good approximation of the physics that we expect. In particular, if you keep a single term here, essentially up to a Hubbard-Stratonovich trick, this becomes the gross Witten-Vadia model. And if you keep the second term, is a nice correction, and already with two terms you obtain a very good approximation, for instance, of the Hawking-Page transition between AdS5 and the black hole. Another interesting expansion that has been noticed is a giant graviton expansion. And here is the form in which you can write the index. So in this expression, the first contribution is the contribution from a Kaluza-Klein gas of gravitons in AdS. This term here instead describes giant gravitons. So in this sense, this is an expansion in giant gravitons. In fact, this object here is the index of a gauge theory with three gauge groups, UN1, UN2, UN3, with some bifundamentals. And in fact, the bulk interpretation of this object is the following, that the states, the BPS states in AdS, can be reproduced by giant gravitons. These objects are D3 branes that wrap an S3 inside S5, and there are three different ways that you can do that. These three S3 intersect, so the three different S3s give rise to three gauge groups, and the intersection give rise to bifundamentals. And the claim is that if you count all the states from all these giant gravitons, you reproduce everything. From the point of view of the index, the contribution of this giant graviton corresponds to single trace to trace relations, or if you yes, let me just take 1 minute. Or if you prefer the operators constructed with the determinant with the epsilon tensor, in fact, when the size of the operator is smaller than n, this is essentially described by the giant gravitons and doesn't know anything about n. The dependence on n appears when we have n fields in your string, in your trace, because then you have trace relations, and their contribution is precisely captured by these giant gravitons. Now notice that in this expansion, there are no black holes. So the claim is here just the gravitons and the giant gravitons capture everything. The black hole should be already contained in this expression, and in fact, this expression can be studied at large n, and this group of people were able to reproduce the black hole entropy from it. Okay, now from the point of view of the bulk, one can do much better than what I described, because as we heard in the talks of Luca Elieso and Juan Maldacena, one can study the quantum mechanics of BPS, but also near BPS black holes in great details using the near horizon AdS2 region and the effective theory, the Schwarzschild-like theory there. And so natural question is whether one can see this analysis appearing from the boundary quantum field theory. We saw this very nice plot in which there is a concentration of states at the BPS point, then there is a gap, and then there is this nice density of states with a particular shape. It would be very nice if it was possible to reproduce this from the boundary theory. And this is, of course, an open question. Okay, so I would like to conclude with three open questions. I already mentioned some direction before, but three open questions that I think are interesting. So one is about going beyond supersymmetry, and it is related to what I just said. So it will be very nice to push this program beyond supersymmetry. So one could try to go to near BPS, and some work has been done in this direction, but I would say that a lot has to be done. We don't have a compelling picture from the point of view of the boundary theory. Alternatively, if we really want to go very far from supersymmetry, probably we have to resort to numerical methods. And in fact, there are very nice works in which one can do lattice Monte Carlo computations and reproduce results, for instance, from gravity or in some other regimes. Another interesting question is about the classification of solutions, BPS solutions in the bulk. So there are indications, as I told you, from the index that potentially there are new contributions. And in fact, in gravity, various people argued that there should exist new supergravity BPS solutions like hairy black holes or multi-center BPS black holes. But these works are either numeric or only perturbative results. So it will be nice to get a unified picture that put together these directions. And finally, I talked about many different contributions, but one would like to put all these contributions together and resum them. Usually these are non-convergent series, and so there is a nice resummation that has to be done. And in particular, this is necessary to do if you want to capture phase transitions, because one has to understand in various regions of the parameter space which contributions dominate. Now, of course, one way to do this resummation is to use a different description in which this resummation is already done, and there are just a few contributions. And in fact, this truncation of the Platistic exponential does precisely that. However, I think it would be interesting to understand how to perform this resummation. There could be some interesting mathematical structure there. And with this, I will conclude, and thank you for your attention.
Thanks for the excellent talk. We have about 5 minutes for questions.
I wanted to. Is this on? Okay. I wanted to ask about this giant graviton expansions. So you said like there are 3 different ways of putting these 3 branes, but I thought in general there are like there is a continuous moduli of these 3 brane solutions.
Yes. So this modular space has not been quantized, but the result of this formula that's been checked up to some order says that essentially this problem of summing all the contribution from the intersecting branes precisely captures what should come from the quantization of the modular space. This problem of quantization of modular space have been addressed for more supersymmetries, and already with 1/8 supersymmetry, it's difficult and has not been done to the best of my knowledge in full details. So that problem is difficult. Here one should take the modular space of 1/16 BPS branes that exist. So that will definitely be interesting to do. But this formula seems to be correct. So there might be some nice intersection theory that one can cook up on this modular space, maybe some localization that could explain this formula. It's for sure a very interesting question.
I have 2 questions. One in the AdS4 solutions, you showed us this interesting formula for the corrected answer, but that was for field theories on higher genus surfaces. Is there a similar formula for the sphere, just the sphere?
That formula is also for the sphere. I think that formula is not correct for this is what they claim in the paper, is not correct for the torus, but is valid for the higher genus, but also for the sphere.
I see.
Yes, and this formula contains all the chemical potential, so it contains everything.
And can I jump in for a follow-up on that?
Sure.
Is there a physical insight for why it switches between the sphere and the higher genus?
Say again?
Is there a physical insight for why the sign switches between the sphere and the higher genus?
Why there is?
The sign switches. You have like 1 minus.
Well, essentially because the Euler characteristic appears here. Yes, so that is essentially the reason. This is the grand canonical partition function. So it's yes. So the sign flip is okay. It's not leading to any inconsistency. When you compute the entropy, you're gonna get because the point is that this formula is written in terms of let me say what I wrote is 4 chemical potentials, but there is a constraint. So in all these games, one uses one more variable and with a constraint, because this allows to write more easier expressions, but there is a constraint. So the genus also appears in the constraint, and once you go, you have to do a constrained Legendre transform. When you do that, there is not just a sign flip in the entropy. The entropy is positive in both cases at the end of the day.
I wanted a broader question. That if I understood correctly, in matching with the entropy, the solutions that are obtained by looking at the index are complex saddle points. They're not directly the Euclideanized black hole solution. There are other supersymmetric solutions, but they're not the original black hole solution one started with, whose entropy was computed semi-classically. Is it understood why this is the case and how one might actually latch onto the black hole solution directly from a field theory point of view?
Yes, I mean, of course, more can be said, but this is very similar to what happens in AdS3 and the fairy tale story. So first of all, there are two solutions that corresponds to or are related to analytic continuation from Lorentzian, and this is the AdS and the black hole. This in the case of AdS3 gives you the two special cases. However, if you just do analytic continuation of the black hole, you find something with an infinite size for the thermal cycle because it's extremal. So now if you want to match with the partition function of the boundary theory, you have to make it at finite size. And this operation, which is also necessary, well, it's not necessary, but it's a way of regularizing the bulk solution in order to compute the on-shell action. When you make it finite, it cannot be just the analytic continuation of the black hole. And what happens is that it is a supersymmetric solution, but they get complexified, but is continuously connected with the black hole. All the other solutions are not continuously connected with the Lorentzian solution. They provide non-perturbative corrections, but it's the same thing that happens in the fairy tale story in AdS3.
Any final question? So if not, let's thank Francesco again.